So who? Okay, so here we are. Especially if you've been keeping up with the extra credit on the exercises, you actually know a pretty reasonable amount about dark matter. It's a little bit of self-investigation, but this is the full story. And this is part of a larger picture that what we're doing is we're just pulling the same stunt over and over, where we learned a lot about our terrestrial planet, and then we used it to infer some stuff about all of the terrestrial planets. We used some stuff about our solar system to kind of guess about other solar systems. We were, in large part, wrong about that. We used stuff about our star to infer stuff about all stars. Looks like we're pretty good about that. We made things like the HR diagram, but we basically started with our star as a model. So we're going to do the same thing with galaxies. We have our galaxy as a model, and we're going to do things like try to make a galactic HR diagram and ask some physics questions that we'll get to in a second. But the first question, which sounds like it might be the lamest question, turns out to be the hardest one. So that's the story of dark matter. But this is a deep field, so this is a field of galaxies. This is what happens when you try to point the Hubble Space Telescope in a place where there are no stars, and you let it sit there for 11 days or so, just collecting light, collecting light. So think about that for a second. I mean, this blob might be, 20 photons. So that's one packet of light coming every day or so from this, 8 billion light year distant thing. And so that's a star, and maybe that's a... So that's a star, and I think everything else is a galaxy. Okay. So our task is a little bit harder in the sense that stars, they had different colors, and we had to deal with that. And it turns out it was related to temperature. But there are actually a couple of things going on in this field of galaxies. So what do we need to explain when we get like this, classification scheme of galaxies? It's probably not going to suffice to say like some are a higher temperature than others. So what do you notice about the differences in between them? We can like zoom in on a big box of close ones to make it a little bit more concrete. Yeah, so their orientation, this wasn't an issue with stars. We've got some, certainly the spiral galaxies, we have face-on spirals and edge-on spirals. Good. Are they all spirals? Yeah, this one looks like a blob. This blob has one of these blobs, I don't know because it's hard to tell, and it might be this one. I think this is the one. So it might have 1 trillion stars in it. It's a freaking monster. That's the one I think it is. So some of them are completely formless, some of them are spirals, some of them are things that aren't quite spirals, and then some of them are none of the above. So as well as different colors, they also have different morphologies. So we're going to struggle to create something that's like a HR diagram for galaxies. We'll use the thing that Hubble gave us. It really doesn't mean anything, but it's just a scheme. But we'll get to that on Wednesday. So what other questions could we ask about galaxies? So same kind of things we asked about stars. And we'll try the easy one first, or so we think. Evolution, so like evolution, what the orbits do, things like that, yeah? Anything else? Good. Let's think about the stuff we asked about stars. So we would have a reasonable hope of actually figuring it out. Yeah. Formation story, yeah, good. Anything else? Composition, good. So maybe that has something to do with color, right? So it looks like some were red and some were blue and some were kind of a little bit of both. Good. You guys are missing the easy ones and get all the complex ones. That's good. Temperature, right? So can we just say some are like hotter than others, for instance? What else? Total luminosity, like total power emitted, which would help us find things like distance. I, for instance, mentioned that this had almost 1 trillion stars in it, and this little sneeze over here has, maybe 1/5 as many as the Milky Way galaxy. Do you think they're the same physical dimensions? Nope. So we could ask about size, and related to size would also be what? density, and then those two things, mass, right? Stuff like that. Good. So we got, let's see, mass, last composition, good. Chemicals, it made of stars, dust. Types, morphologies, ages, did they all form at the same time? I guess we missed that. And evolution and things like that. Yeah. And then maybe we could ask if they die. So stars died, and it was pretty interesting. Maybe galaxies like spin themselves apart. And then what they do with their orbits. I think that's everything. Good. Okay. So, and then finally we'll pack things into something that kind of looks like the HR diagram, but isn't really, and it kind of sucks, actually. But we'll start with mass, because we know how to do this, and you guys spent a couple exercises doing it. And it seems like it just requires a little bit of a modification. So how do we find the mass of Mars, for instance? And there's, I guess that's Phobos, I don't know. Maybe it's Deimos. So in the most specific way possible, as if somebody were to ask you a question on the final exam that was how do we determine the masses of planets and stars? Yeah, you need to have something orbiting it, and specifically, what two properties of the orbiting thing do you need? So mass is what you find. So you need the distance in between and the time it takes, yeah. So you need the distance at which it's orbiting and the time it takes. And that's Kepler's law, and Kepler didn't know what we did to his law. He would have been shocked, because he was just talking about planets around the sun, and we used Kepler's laws, namely that the distance and the period of orbit will tell you the mass of the thing that's pulling you around. We used it to do all sorts of stuff. So we took it way outside of its comfort zone. Good. So we can do this, and we found the mass of Mars because Mars had Deimos, and the orbit of Deimos was like a day and a half or something like that. So that's not a problem at all. And then we weighed stars, and we did that. It took, sometimes up to years. So these are, I think, radio observations, and there's a star and there's another star orbiting in it, and you see like June 96 to May 96. This is going to take about a year or so. So we can do that. And we're given the gift that 50% or so of stars are in binary systems. So you just find a star of the appropriate spectral type, and then find an orbit, and find the distance, and find the measure the period, and then you have it. Okay, so we'll just say that takes years. Okay. Technically, mathematically, in principle, we could do this for galaxies. What's the problem with weighing galaxies? So I'll pick a star. I'll pick a star out at the edge where I think I've got all the mass inside of its orbit. And how long do I have to wait for the star to orbit the galaxy? That's one problem. I think this is a number that got thrown around in like week 1, and then we returned to it really briefly. Quarter of an orbit ago, we had dinosaurs on Earth. So a full orbit takes about 230 million years for us. And we're in the suburbs. We're not even like way out in the sticks. So that's one problem. Problem 2 is that, once you decide to go vegan and live for a quarter of a billion years and observe your star, so how on earth are you going to see a single star out at the edge of this? So this idea works in principle, but in practice, we can't just sit there and wait and observe a single object. But we do know this. We know that like the motion of the things will tell us the gravity that's affecting them. We just don't really want to wait for 250 million years for a single star to orbit its galaxy. Okay. Yes. So you can do that, and you are now in the physicist camp. So how this problem was solved in practice was basically like the galaxy weighers split up into 2 groups, and there were the astronomers, we'll make that you guys, and then the physicist. Now that's you guys. And the physicist said, I don't need to wait for a quarter of a billion years. Let's say that I wanted to know how long somebody was going to drive around a circular racetrack. I could just maybe take a radar gun, and I could figure out how fast they're going, and then I could look at the radius of the track. And if I see their speed and I know how long it's going to take, I can do some pretty basic math and figure out the period. So I'm not going to wait and measure a full lap. I'm just going to measure their instantaneous velocity and use that to extrapolate. Yeah, good. The astronomer says, that smells like physics. I'm not going to do that. What I'm going to do is I'm going to count the stars, quote unquote. It's more sophisticated than that. So you kind of look at our own galaxy and close by galaxies, and you make an estimate of how many kilograms it takes to make like some number of watts of light. So this mass to luminosity ratio. And then you figure out the luminosity of a distant galaxy, and therefore you infer its mass. But philosophically, it's counting the stars. And one way or another, you have mass, and therefore you can back out the, you determine the force through the acceleration, and you're able to back out the mass. Okay. People okay with that? Okay. So in more specific detail, the physicists, the method 1 people, this is what you're doing, is there's velocity. So in tangential velocity, as a star is orbiting the center of the galaxy. And so, for instance, maybe it's coming towards you at this point and away from you at this point, and this would be, the center of the galaxy, and the string would represent the gravitational force. Is at point A, as this thing is moving towards you, you would notice the star to be a little bit blue shifted coming towards you. And here, as it's at point B, it's moving transverse to you. So just like the exoplanets that move side to side, you see nothing. So this would be neither blue shifted nor red shifted. And at point C, as it's going away from you, it would be red shifted. So you actually have a pretty easy way of measuring speed. So you just put some little shutters over the part of the galaxy that you care about, and you can measure its instantaneous velocity. And once you have the velocity, you can do a little bit of, like physics 1 physics, and figure out the force required to keep that thing in orbit. And once you have the force, you can back out the acceleration. Sorry, once you have the force, you can back out the mass. So it's okay? Okay. So it's really just measure the speed, and you can figure out how long it took to orbit. These are the details, but the essence of the method is figure out how fast this star is coming towards you and away from you, and then you could figure out how long it would orbit in principle. So it's like kind of a proxy for waiting for an entire orbit, is just look at the speed and say, figure it out, dump it into the equation. And once you find how long it takes to orbit, you can do this. Okay. And now we have a tool to do that in the Doppler Shift. Okay, so let's do that, and here's a big picture of a spiral galaxy, and maybe let's make a curve that we think the stars should obey. So forget about the supermassive black hole that's sitting there, or just think about the supermassive black hole itself. But plunked right down in the center of the galaxy, how fast should this thing be moving as an orbital speed? So should it be coming towards you or away from you relative to the whole galaxy? Is there any mass inside of its orbit? It's the thing that's actually at the center. So right at the dead center of the galaxy, what should I see or not see? Yeah, so stationary. And maybe the galaxy itself has like what's called a peculiar velocity, so the whole thing's moving towards or away from you. But this thing doesn't have any mass inside its orbit. It's right at the center, so it's got no speed. This is what we would expect. And then as you start moving out in this direction, let's say that we're spinning this way. Say we're spinning this way, so we're positive. So I get more and more mass inside of my orbit, so what should happen to my velocity? Is it possible to go down from 0? No. So it's got to be something, right? And as you have more mass enclosed in your orbit, you should get more velocity, greater acceleration. So as I go from center farther and farther out, what do you expect to see from the speeds of these things? So we're looking at speed versus distance from center. Yeah, something going up, right? And then now we're out in the suburbs, and our distance from the center and most of the mass is starting to get big, and we're not compensating for it by putting more mass inside of our orbit. So as I get out in the suburbs and then kind of the sticks, the tundra of the galaxy, then what's going to happen? Slow down. And then eventually what I should get is kind of a 1 over r squared, if you're kind of a real aficionado, is when I get really far away from this. So for instance, we don't care about the Andromeda galaxy's gravitational influence. So when you get like out here, it should go off towards 0. Okay. And then on the other side, just because it's spinning in the opposite direction, I would expect to see this be symmetrical, but negative instead of positive. Does people have any reservations about that? Does it seem kind of reasonable? So not moving. As I get farther from the center, I get more mass inside of my orbit, so I'm getting pulled more and more. So I spin faster and faster. And then at some point, the fact that I'm just farther away from everything and I'm not putting more mass inside of my orbit takes over. So this is what you would expect, just based on the luminous matter. And this is what people see. So this is the start of that. So you take a little kind of shutter of the galaxy and you look at this and it's moving towards you. So it starts out pretty slow and then rises to something. And then here we're out in the suburbs. We're kind of leveling off. And then let's not talk about this yet. But really it's relying on Doppler shift towards you or away from you. Okay? So clever, right? And this is why Doppler shift is so important. Method 2 is really just count up all the stars in a kind of sophisticated way. And maybe you would expect these things to, I don't know, just ask, do you expect these things to agree? How well? At all? I don't know. It turns out that they don't agree, and it doesn't look as bad here. So this is what we did, is we kind of said, well, at the center, nothing should be moving. There's no mass inside my orbit. And then as I get farther out, I get most of the mass inside my orbit. More mass inside my orbit means I'm pulled faster. And then as I get farther out, I should level off. What you actually measure, now this is with the Doppler shift, so this is the actual measured rotational velocities. You go up, and you stay up. And you never come back down. This is very weird. So it doesn't look like such a bad discrepancy, but when you actually, kind of take into account the math and the fact that this orbit is including, kind of r squared area, so it makes the effect really pronounced, is that in order to make these things agree, what you have to do is you have to put all this matter that doesn't shine light, so, come up with a clever name for that, all this matter inside the orbit. And for every star or amount of shining luminous matter, basically to make this curve, you would have to put in about 5 kilograms of dark stuff for every 1 kilogram of light stuff. So this is like a factor of 500% disagreement. This is not something even astronomers will live with. So these methods don't agree, and they don't agree in a really weird way, is that there's all this matter that not only do we not see, but it doesn't absorb light and it doesn't emit light. Okay. And this isn't just one freaky galaxy that got spun too fast or something like that. This is generic from all sorts of galaxies. So you look at every spinning spiral where you can actually do this kind of sensibly, and what you expect just by looking at the luminous disk falls off like you expect it would, and every single one goes up and stays up. And again, the discrepancy is we're missing 80% of the mass in the universe according to this calculations. So, and it's all distributed in the halo. And nobody has been able to debunk this as some sort of measurement effect. People have been doing this for, at least this method, really conscientiously for about 30 years now. Somebody named Vera Rubin basically made her career painstakingly measuring these things. So this is not a happy circumstance, and this is kind of the inferred picture of what a galaxy looks like. And in fact, it's pretty interesting. Somebody described it to me once as, imagine that you took a shiny penny and you froze it like in the center of an ice cube tray. So you fill the ice cube tray halfway, put the penny in it, pour water on top of it, and fill it again. So you have a penny frozen inside of an ice cube tray. And the shiny penny is the galaxy. And then the kind of clear ice, which is there and it exerts some effect, gravitational effect, is encasing the penny in this shielding matter. So this is the so-called dark matter. And it really kind of dwarfs the galaxy itself. So this must be the stuff that's keeping those speeds so high. Right? So this is our new model of what a mass density of a galaxy must look like. It's a little bit disconcerting. So you would expect to see, so why doesn't it affect the stars at the center? So where would you put this point? Even if there's, so this thing can't go anywhere by symmetry. So you kind of have to have this part of the curve. And even if I took a whole bunch of dark matter, like extra dark matter, and put it at the center, you'll always have no velocity there. It's true that there seems to be an underabundance in the disk, and we can kind of account for the disk properly, which is, I don't know, it's kind of on the edge of what is well enough resolved to be presented in a class like this. But there are some weird effects where it doesn't seem to be as present in the disk as it is elsewhere, but I think that's up in contention still a little bit. But you can imagine it's like encasing the whole thing. There's dark matter everywhere. Potentially there's dark matter in this room. Yeah, so the mysterious kind of fictitious forces of a spinning top are completely understood through Newtonian physics, and you don't have to invoke any like mystical woo-woo matter or anything like that. So people have tried to say that there's a discrepancy in Newton's laws here, or there's some effect, involving Newton's laws that hasn't been quite, that wasn't really established before this, because this whole thing is, 100,000 light years across. So it's not really clear that we should be using instantaneous Newtonian gravity. But so far, nobody's been able to just say, like, listen, this is this aspect of, Newton's laws that you guys just didn't explain clearly or didn't model clearly. And it's really, you're talking about a five-fold increase in the amount of stuff pulling things around. And it extends all the way out, like 5 galactic radii away, 10 galactic radii away. And this is one line of evidence. In fact, your objections are very reasonable. There are like 5 separate independent lines of evidence that this stuff exists. This stuff. This is my picture of dark matter. Okay. So what this really means is, truly think about that dark matter halo, and you've got a star in the middle of it, and we see that light coming from a distant star. So that means the dark matter is in no way affecting that light. So this, 10 galactic radii halo of this stuff, 5 times as much matter, is just letting the light pass through to you without warping it in any way, absorbing it. So it's got to have some pretty peculiar properties. And at the far end of this, people truly think it's like a new form of matter that actually does not interact with electromagnetic radiation. So if you held out your hands and I gave you some dark matter, it would just pass right through it. So it just like wouldn't even interact with you. So this is the dark matter problem, so-called dark matter problem. Okay. So this would be a little bit, if there's one line of evidence, people wouldn't really be too impressed. But you actually see the fingerprints of this everywhere. And in fact, this is one of the kind of smoking guns, this so-called bullet cluster, is that these are 2 clusters of galaxies that are interacting, so they smash together. And, shame on me for not knowing exactly what the composite image is. But the gas and the dust stays behind, and the dark matter flies through. So it's not dust and gas. It's stuff that sticks to the galaxies themselves and passes through normal matter completely unmolested, is what this seems to indicate from this galactic collision. More independent evidence is that if you actually weigh up clusters of galaxies by looking at gravitational lensing, so here's a big cluster of galaxies, and this is a bunch of repeated images of a much further object being pulled around, and you calculate the inferred mass based on how much the light is pulled around. The light is pulled as if, in fact, it gets worse for lensing calculations, is that it must be like 10 times as much mass pulling this stuff. So the gravitational lensing tells you that there's also more mass than you can account just by galaxy counting. So dark matter is definitely present or inferred from lensing. And next, you can't, I kind of wish that we had shuffled up the guest speakers a little bit so you'd seen those talks now and you could ask really nasty, prickly questions, is that you actually can't get a simulation of a galaxy to work unless you add the dark matter halo. They just don't do it. They don't stay put. So the idea of having the spinning spiral flattening out in space, they actually fly apart and they're unstable unless you encase them in dark matter halos. So the luminous matter needs to be in a dark matter halo. And that was totally in those pretty movies that you guys saw. And then finally, I think this was mentioned, is that you actually can't simulate the universe itself on the largest scales without dark matter. So you can't get this like latte foam of the cosmic web of sheets and voids. Each one of these is a galaxy. So these dots are all a single galaxy, and that's Milky Way galaxy there. So this is the total observed structure of, the part that we can see at least, of the entire cosmos. And if you try to simulate this from the constituent stuff of the Big Bang, you don't get sheets and voids forming without dark matter. So you guys saw the really nice simulations. I will show you state of the art circa 1990. So put a whole bunch of particles in a box, and then you let gravity go, and you kind of start seeing this these sheets and voids being formed. They would not do this if you didn't put in the requisite amount of dark matter. So the structures that form, this whole thing's rotating just for visual. So these sheets and then these voids, they don't form without dark matter. You just can't get it to work. Keep going. And this is something kind of like what our universe looks now. And again, each one of these would be a galaxy. Yeah, the box in which they're running the simulation is a cube. So nothing works. It must be there. So at this point, there are 6 or 7 independent lines of reasoning that say that this stuff is there. You just don't get the structure forming, so everything just kind of hangs out and doesn't stick together in the sheets and the voids. So those filaments, those really overdense filaments that you see, they just don't form. Everything just kind of hangs out and clusters a little bit together, but not to the really high degree that people see here. This? Oh, this is real data. So the reason that there are black patches here and here, this is, I don't know, I keep forgetting to mention this because it's kind of like a lovely thought, is that this is Sloan data. So this is from the Sloan Digital Sky Survey, which is a telescope that operates in New Mexico at Apache Point. And this is the stuff that's below the horizon from New Mexico. So we can see, out, this would be like 6 billion light years away. So 6 billion years into the past, in this direction and that direction, but not in this direction because that's over the horizon in New Mexico, and that's over the horizon in Apache Point, New Mexico. And if we had put this in like the Atacama Desert of Chile, we would have seen this slice of the universe and that slice, and not those. So I don't know. Yeah, it's kind of weird, right? But this is actual data. So each one of these is, and the color coding indicates what type of galaxy it is, which we haven't quite talked about yet. So spirals versus ellipticals and things like that. Okay. So now when somebody says this, at least sort of indirectly, can you see the dark matter? Can you kind of infer it's there? What would it look like? It's pretty hard. I mean, it's dark. And you can infer that there's some lensing. So can you guys see like the effect of the lensing from the cluster? Yeah. So I see some lensed objects there, and then something kind of smushed out there, and some streaks there and there. So what you can do, and what people are getting better and better at, is this is another type of computational astronomy, is you take real data and then you try to pull things out of it, is that you can actually say what sort of dark matter profiles would be required to make that lensing. And you can make a map of the dark matter, and it seems to be sticking with these clusters, but then it's really far away too. So it kind of gives a visual key to it, and this is starting to, this is a little bit more serious, technically citizen science than Planet Hunter or whatever, but still something that humans are better at than computers. So there was even like a data mining competition on Kaggle, which is this kind of outsource, like Merck will tell you to give you their data set and figure out who's going to get a heart attack from their shitty drugs and stuff. But they put one up for a hedge fund, actually. It said, find the dark matter. They gave you a prize if you found the dark matter. So it requires at this point, you don't see it and just publish a pretty picture in a paper. So it's starting to get like pretty serious and computational. Okay. So any questions about the evidence for this missing mass problem? Although I think that, seen the missing mass problem before as early as exercise 5. I guess. Okay. So this is not acceptable because we're kind of, dark matter doesn't affect your daily life, but, it'd still be nice to know. This would also be a good time to check in on why we're doing this stuff in the first place. So what is dark matter? Any thoughts, ideas, suggestions, things that you would hate it if it was? Never know. Finger of God, yeah. So there are really kind of 3 classes of ideas, and I'll mention one for historical reasons, although it's pretty much precluded as far as I know, is that this was so straightforward. There's a lesson about, I guess, how scientists work or don't work in this, is that one set of theories is one of the more obvious things that you could possibly imagine is that this is the initial mass function, so you get like a nice big O star, and then you would get maybe 120 M stars for every O star, and that this cutoff had nothing to do with sizes of shreds of gas that collapse into balls. And you could have things that were 6% of the sun's mass and 2% of the sun's mass. Why is it that we don't see them and we don't put them on this chart? Well, they just don't do what? They don't fuse. Maybe they're an infrared. And infrared took a long time to get working. So the idea was that there are thousands and millions of these little pseudo stars, and it's you can't even really decide what to call them. Are they infrared stars? Are they dwarf stars? Are they brown dwarfs? Should really be infrared dwarfs. Are they rogue planets? I kind of like that one. Is the universe just absolutely full of little Jupiters running around? And in some level, I think it's a very nice, even though it's a little bit unexotic way to resolve the problem, is that we're talking about quadrupling or quintupling the amount of mass in a galaxy. And if you remember the grapefruit model, and I'm hopefully totally okay with this now. I have a grapefruit in Seattle that represents, the 1 in 10 billion scale sun, and then the nearest star to us is where? Yes, tangerine in New York. And what we're honestly really talking about is hiding like 5 more citrus fruit in between here and New York. If I hid 5 citrus fruit in between here and New York, do you think you could find them? No, it's hard, right? It's kind of difficult. So maybe scattering some of these things out there. So this is a really popular class of theories. Astronomers love these theories. They get swept under the banner of massive compact halo objects. They have mass, they're compact, they've been squished into little balls, and they float around the halo. They got ejected from stars forming and stuff like that. And it's so sensible, and the acronym they came up with is, of course, MACHOs, massive compact halo objects. The dark matter is just the fact that there's a whole bunch of stuff out here. You just can't see it, because if it shines in infrared light. And it took a long time to get good infrared telescopes. In fact, one of the first ones is from the late 1980s, and it expected to see the sea of these things, and actually didn't, which was a real big setback for the macho men and women. Okay, machos. Idea 2, this is kind of favored by particle physicists, so is that it's truly an exotic type of massive particle, and it just literally does not interact with electricity or magnetism, aka light. So the massive neutrinos is one, so there's an absolute sea of neutrinos floating around. Things called axions, people just make up some particle name and then say it's got these properties and we'll fit it into the standard model of particle physics, and they truly, literally don't couple to light. You have a box of axions and you shine a flashlight through it. Even though it's pulling you with a little bit of gravity, it's got nothing to do with the light. These this class of theories. They're not a single thing. So this really means that it's absolutely nothing on the periodic table, none of the quarks and neutrons and protons that contain them, nothing that you've ever seen before, like something that's truly new. And this class of theories, this tells you something about how much certain people might need a life. They named their class of theories or swept them under the banner of weakly interacting massive particles. So the weakly interacting is in it doesn't interact with light. And the acronym there, of course, would be, to contrast with the machos, the WIMPs. This is the one that people tend to prefer at this point, just because the infrared astronomy just didn't see the machos. But there is something deeper here, is that the astronomers tend to prefer the macho theory. Why is that? What do they want? Money for a new telescope, right? The particle physicists tend to prefer WIMP theories. Why is that? Want money for a new whiteboard? I don't know. There's kind of a saying that if you're a hammer, all your problems are nails. So this doesn't really reflect like the wisdom of people in the scientific discipline. It's just like, it's very visceral. I want this to be true because like I do particle physics. It should be a particle. And there's these people, I don't know why, but they're kind of on the lunatic fringe. This seems like a reasonable thought too, is that we're just not doing gravity correctly. And either Einstein's theory of gravity doesn't quite work on these big time scales, or distance scales. It's only 100 years old, and this thing takes 100,000 light years, and therefore years to cross. So maybe there's some correction, or maybe quantum gravity has something to say about this. For some odd reason, the let's just fix gravity people, I don't know. So I think you just go up against quite a headwind if you're trying to like overturn the work of Newton and Einstein. It's like, who are you, or something, I don't know. But those are the three big ideas about what dark matter is. But what you can infer from that is, do we have any idea what dark matter really is? No. Okay. Do you care? Does it affect your life in any way? On a day-by-day basis. Okay, so why are we doing this? So maybe this is a good time to check in a little bit. So astronomy basically started as a very effective timekeeping device, so people would know when to like plant stuff and go out and look for certain seasonal crops, I suppose, and when to sacrifice virgins at Stonehenge, things like that. And then it became somewhat politicized with certain groups of power could predict eclipses, or you were challenging their worldview, so maybe they burned you at the stake. And now why are we doing this? Because it's about to get pretty, make us feel pretty insignificant. So things have totally flipped. So it used to be that you would perform experiments on Earth to explain the motions of the heavens, which is still to some degree true, but we don't really have too many things on Earth that, on a deep level, at least that astronomy can explain to us, need explaining. So now things have kind of gone backwards, and now we look for exotic things in the heavens to suggest fun experiments to do on Earth. I like this picture. This is at UW, and that's Don Brownlee, who's an astronomer, so he'd be a macho person. That's Dr. Leslie Rosenberg, who's like one of the premier axion experimenters. And this frozen trash can is an axion detector. So I think it gets filled with liquid helium or something like that. And it's got a huge magnetic field. And it's just waiting for these weakly interactive massive particles to come in and decay or get sucked to the side or do something. And they haven't seen any of them. So, people have kind of precluded the massive compact halo objects, but I've yet to see a good indication that the particle people have it right. So it's really an open question. So, any questions about that stuff? This may or may not be resolved in your lifetimes. I don't know. Yes. Oh, it gets worse because there's this thing, right? And if there's a leak in the in the refrigeration, or some like a marmot chews through one of the wires or something like that. Yeah, I mean, we'll put numbers on this, but at this point, so for instance, CERN, which is really just at the high end of scientific experiment for its own sake. How much money are you paying for this? Do you think it's a good idea? You know, we've kind of gone to just something that's akin to pure curiosity. If you read the CERN website, I don't know what Dr. Rosenberg says, but if you read the CERN website, they say that they'll have some like medical, I don't know, some derivative technology, or they'll advance medicine in some way. And I hope not. I hope you don't have such a bad bout of cancer that you have to put your leg inside this 30-kilometer particle accelerator or something like that. But yeah, I don't know. So that's up to you guys to figure out. But again, we'll put numbers on budgets for space exploration and science at the end of the quarter. And I will tell you that there are many more wasteful things, at least in the United States federal budget. So, other questions? Yeah. So this is interesting because, so does dark matter have a temperature? Yeah, so the formal physics definition of temperature is something to do with the kinetic energy of the molecules. So if you have like a cold glass of water and you heat it up, all the water molecules jiggle more, so the temperature goes up. There are two ways of determining the temperature of something in space, one of which is the black body spectrum. So you're going to see a black body spectrum of dark matter? No, it's got no light, right? So the other way of potentially figuring out its temperature is to have it come to thermal equilibrium with something else. So take the dark matter and stab a thermometer into it. But technically it's actually, it's coming to equilibrium with the thermometer by giving it light and bumping into it. And dark matter does none of those things. So if dark matter had a temperature where the dark matter particles and clumps of dark matter are wiggling, I don't know how you would find that out. So could be, I don't know. So little is known about it. I mean, whether or not it's comes in lumps that are kind of like solids, and whether it's like totally uniform particles. It's actually only recently that people had the revelation that dark matter might not be monolithic in the same way that the periodic table is all sorts of exotic stuff. Yeah. Yeah, they're little Jupiters and super Jupiters, the machos are. And it's not that they obey like exotic goofy physics. It's just that they're so small we don't see them. So the light is passing around them, but then if you imagine the cross-section of Jupiter and the scale of a galaxy or something like that, it's just like, oh man, that's just not a lot of space to, So you take a lot of matter and you just squeeze it into a small area, and therefore the light that you think would have been blocked just totally misses it. You're just like scrunching it up. But you would expect to see them radiate in infrared, and that hasn't happened yet. So I don't know, maybe they cool too fast or something. Who knows? But potentially, yeah. So one way or another, there's mass that you can't see. Whether it's normal mass and it's just hidden in a clever way, or if it's truly something new. Yeah. Other questions? Yeah. No, dark matter technically doesn't have any. You can have black holes made out of just normal matter, and this is where it gets annoying because there's this stunning lack of creativity among the astronomers in naming their interesting things. So your textbook makes it worse because it puts the dark matter and the dark energy in the same two sections, and dark matter is I wouldn't say it's well understood, but it's a very well scoped out problem. And you couldn't find somebody who's like, I don't believe in dark matter. There's so much evidence. Dark energy is a very new thing. And while dark matter keeps galaxies together in clusters of galaxies, cosmologically short spatial scales, dark energy acts on the longest scales of the universe. So it's something that's pulling distant galaxies really far away. And black holes are dark too. And it's just, could we rename one of them, like mystery ether or something for dark energy? Just give it a name that's not a little bit confusing. But no, I mean, you can make a black hole with just normal matter. You just got to crunch it up until it's got the critical density and falls through an event horizon. Yeah. Little guys. So these would be machos, massive compact halo objects. They got mass, they've been squished, and they live up in the halo. And they're objects. No, so these are emitting red light to blue light and a lot of infrared too. So those are things that you could see. So it wouldn't be dark matter. And that's the matter that we are counting up. But it seems like for all of that stuff, there's 5 times more, I don't know, in the cosmos. Yeah, the only thing that people really know about the inter-halo stuff is that they seem to merge, and it's almost convex, like you get 2 galaxies together. It's almost as if they make more dark matter, in the sense that the lensing from clusters of galaxies says that the dark to luminous matter is 10-to-1, where a single galaxy's rotation rate suggests it's about 5-to-1 or something like that. Yeah, it seems to merge. If you had like 2 coffee spills, that's the theme of my quarter. If you had like 2 blobs of coffee on the table and they ran together, that seems to be what the dark matter does when you have, multiple galaxies. Yeah, pretty strange, right? I don't know. So people will figure out more during your lifetimes, I hope. Other questions? Is on a quiz?